11.8 Volumes by disk and washer methods. First of all, you will see the word revolve. Revolve is the verb for revolution. Revolve means to go around. For example, we know that the Earth revolves around the sun. The Earth goes around the sun. It makes a circle around the sun. So here's Earth, there's the sun. So that's what revolves means. Okay. Now we can make solids when an area is revolved around the x or the y axis. For example, here is f of x. So here we have a line.
Now imagine what you would see if you...
What happens if we revolve this line around the x-axis? When we do that, we make a solid. So from a different angle, so if we look at the angle, this line, when our line is farther away from the x-axis, it's going to make a bigger circle. When it's closer to the x-axis, it makes a smaller circle. You add all of these circles together, we get a solid that looks like this. Our goal is to find the volume of this solid. Okay. How do we do that? This is called the disk method. What is a disk? Well, disk, also spelled D-I-S-C, looks like a frisbee. So here's an example of a disk. It's what happens when you revolve a circle around the x or the y axis. Going back to our simulation. So this line f of x revolves around the x-axis, making the solid. How do we find the volume? First of all, each cross-section is a circle. So this solid is the sum of all of these cross-sections. Each cross-section is a circle. So this tells us that we're going to integrate. We're going to be integrating the area of a cross-section. We have to do that. Times dx from A to B. So we know we're doing that. How do we find the area of the cross-section? Well, the radius is just f of x. This is a circle. The area of a circle is pi r squared. So the area has to be pi times f of x squared. In other words, the volume would be pi times our area of cross-section. Will just be the area of cross-section. Yeah, and this area, is really pi times our radius squared. And again, the radius is f of x. Okay, so the volume would just be the integral from a to b of pi times f of x squared dx. We're adding up all the areas of each of these disks. Okay. That's why right here, the volume is given by this formula. If we have a function g of y that revolves around the y-axis, and it works the same way, the volume will be the integral from a to b of pi times g of y squared dy. Example 1. Region R is bounded by the function f of x is equal to negative x to the fourth plus 3x cubed minus 2x plus 4. The x-axis and the y-axis. And We know that region R is in the first quadrant, so it means that x and y are both greater than 0. We're told that f of x equals 0 at x equals 2.926. So what's happening? This area R is going to be revolving. Each of these disks are going to revolve around the x-axis, making a circle. We want to find the volume. Okay. So the volume has to be the integral of pi f of x squared dx from a to b. Well, a is 0, b is 2.926. Pi we can move to the front. F of x we know is negative x to the fourth plus 3x cubed minus 2x plus 4 times dx. Okay. We can use Wolfram Alpha, use our calculator to calculate our integral. Okay. So we're doing integrate negative x to the fourth power plus 3x cubed minus 2x plus 4 from 0 to 2.926. The calculator integrates for us. There's an extra equal sign there. So we're integrating. And the calculator gives us 101.011. Be careful. I made a mistake and I made the typo. It's negative x to the fourth, not x to the fourth. So it's really 15.222. So that means that this is equal to pi times 15.222. Really is approximate. So 15.222 pi 0.222 times pi is about 47.821. So the volume is about 47.821. That's it. Okay. Next, this time our solid is not just generated by the area between f of x and y equals 0. Instead, we have f of x and g of x. So let's look at our simulation. So here we have y equals f of x and y equals g of x. Two functions. They're always positive, and f of x is always greater than g of x. We can revolve this around the x-axis. When we do that, like this, so this is revolving around the x-axis. When we do that, we're going to get a solid that looks like this when we rotate. Okay. This is called the washer method because washers look like this. Here's an example of a nut, and here's an example of a washer. So that's why this is called a washer, the washer method. So here's the washer. Again, it's formed from rotating like this. But we see that there's a hole in the middle of the washer because the region. So what we're really doing is this region gets rotated, but the region below g of x, so the region between g of x, the region between f of x and g of x are rotated, but this area between g of x and y equals 0 does not get rotated. Okay, so this area does not get rotated. So how do we find the volume? Okay, well, if this was just a disk, we know that the volume would be pi f of x squared dx. But here, our area is not f of x, it's f of x minus g of x. So some people might think, oh, I can do that. So in other words, the volume must be pi times the integral from a to b of, okay, f of x minus g of x squared dx. Be careful, that's not correct. Okay. Instead, what we're really looking for is we're looking for f of x squared minus g of x squared, because we're subtracting the volumes, not the area. Why? Because when we're rotating it, we have the volume of the big thing minus the volume of the small thing. We have the volume of big minus the volume of small, which is equal to pi r of the big one squared. So we can factor out pi minus r of the small one squared. But that's not equal to pi of r big minus r small squared. So just be careful. Okay? So that's wrong. That's right. So once again, then going back to our presentation. So that means that each disk must have area pi of f of x squared. So the volume is the integral from a to b of pi times parentheses f of x squared minus g of x squared close parentheses dx. We're subtracting volumes, not finding the volume of the difference between the radii. Okay. All right, let's look at a couple of examples. Example 2. This is from the 1999 AP test, question 2. The shaded region R is bounded by the graph of y equals x squared and the line y equals 4, as shown in this figure. So we have y equals 4, we have y equals x squared, and we have this bounded area region R. So this is R. Okay. We want to find the volume of the solid generated by revolving R about the x-axis. So this thing is going to be revolving around the x-axis. We're going to use the washer method. First, let's figure out the endpoints of our integration. Since y equals x squared, that means that x equals the square root of y. So, since we're looking for the endpoints, we're not looking for the inverse. Y equals x squared, and y equals 4. So x squared equals 4. So x is equal to minus 2, and x is equal to positive 2. So our endpoints are negative 2 and plus 2. Okay. So the volume is going to be, we factor out pi out front. The integral, pi times the integral from negative 2 to 2 of fx squared minus gx squared dx, which is equal to pi. We integrate from negative 2 to 2. F of x is the top one. It's just y equals 4. So it's just 4 squared. Minus g of x is x squared. Squared. Dx. Okay. We can just evaluate the integral right away. We can use a calculator. Or we can simplify further. If we do, it's pi times the integral from negative 2 to 2 of 16 minus x to the fourth dx. Okay. Let's go back to root from alpha to integrate this. So we want the integral of 16 minus x to the fourth from -2 to 2. So the integral gives us 51.2. So this is equal to 51.2 pi. And 51.2 pi is approximately 160.85. And that's the volume using the washer method. Okay. Once again, I have the notes here that's typed up and more clear. Final example. Same region. Same shaded region R, bounded by the graph of y equals x squared and the line y equals 4. But this time we want to find the volume of the solid generated by revolving R around the y-axis, not the x-axis this time. So we have this, and we're going to revolve around the y-axis. First of all, I want to point out that we really only need to use half of R, the right half, the one above x equals 0, because when this revolves, it's the same thing as the whole thing revolving. So we're really just looking for this region for this problem. Our limits of integration is going to be from y equals 0 to y equals 4. And our function, well, y equals x squared. So that means that x equals square root of y. So that means that g of y is going to equal to the square root of y. So our volume, this time we can use the disk method because we only have one function. The y equals 4 becomes a boundary that we're integrating. It's got to equal to pi times, we're integrating from 0 to 4 of r squared. R squared is, the r is g of y squared dx, dy, not dx, which is equal to pi times the integral from 0 to 4 of square root of y squared dy. The square root of y and the square root cancels, so it's just pi times the integral from 0 to 4 of y dy. This one we don't need a calculator for. So that's equal to pi times 1/2 y squared, evaluated from 0 to 4. The 0 square is 0, so we only need the 4 term. So it's pi times 1/2 times 4 squared, which is 8 pi. So if we revolve around the y-axis, the volume is 8 pi. Okay. That's it. Once again, I've typed up the notes for you. Summary, what did we learn? If we have an area R bounded by f of x and the x-axis, then the volume is equal to the integral from a to b of pi times the square of fx dx. That's called the disk method. If this were bounded by y-axis, then we will be integrating f of y squared dy. Next, if an area R is bounded by f of x and g of x, and let's say that f of x is greater than g of x, then by the washer method, the volume is the integral from a to b of pi times the square of fx minus the square of gx dx. So that's it for this video.